Hello and welcome to this demonstration. In this video, we will see some enriched features of the results mapper in ANSA, where we have added some meta-advanced capabilities in order to expand the range of available results. We have prepared 3 sample cases in order to showcase these new advances. The first one is a temperature mapping from a transient heat transfer to a thermal structural simulation. The second case is a pressure mapping from a CFD to a structural simulation. And the third one is a stress mapping from a dynamic explicit forming to a static structural simulation. Let's quickly start with the first case. We will first review it in Meta, and then we will see how we can directly map these results inside an ANSA structural mesh target. The first thing is we see that the initial simulation is a transient heat transfer. It starts from 20 degrees at this base, and it ends to roughly 800 degrees. We can pick any one of those time steps. Let's say time step 76 will be the one that we will use. And we can see how we can map this temperature field to a target in ANSA. We only opened Meta to review what is inside the database that we will read the results from. You do not actually need to launch Meta. You can directly access the results from within ANSA and the results mapper. As a target, we will use the ANSYS deck. So we have switched to the ANSYS deck here. And we will go to the Structural tab and activate the results mapper. The results mapper window opens, and we switch the source to the new solver files format. In this way, we are able to directly access the result output databases from the same or from a different solver. Here we will pick the ODB file, which is an Abaqus output database, which we will use as the source. Once we select the solver result file, we click on Scan Solver File. During this time, Meta is launched in the background and it is scanned for any available data labels that are inside. Also, if multiple states are available inside the file, we will see that we will be able to pick which state we can take the results from. Here, there are different steps of the transient simulation. We can go directly to the one that we want to transfer data from. And in the custom mappings, we can right-click and click Add in order to take one of the result labels that are found inside this file. 3 types are available: scalar, vector, and tensor results. According to the different categories of mappings, we will see that different scalar labels will be available here, or vector labels, or tensor labels. Here we just need to map the scalar nodal temperature result, and we see that there is a label called NT11 directly available. The target is going to be either a result entity or a boundary condition. For this case, we want to build a boundary condition. We will see result entities later on. The type of entity that we want to create is either stress, temperature, or pressure. Here we want to create a temperature entity. And since we are mapping from a solid mesh to a target shell mesh, we need the RBF function. We will expand the search distance to twice the initial, so it will be 2 times local average, because of the target mesh is quite fine. And it has very small element length related to the source. In connectivity, we have to pick by typing a question mark in this field, and we can pick from the screen the target properties that we want to include in this mapping. We don't need to reorient anything, so we will switch off the reorient option, and if we click Apply, the result is mapped and we can review it either by looking at those BF entities that were generated. We can pick one of those and we can see that we get a value. Or we can more easily activate a fringe plot for temperature. We can go to element temperature and activate this fringe plot. Now moving on to the second case, we will first review it in Meta. Here we have already loaded the source model of the second case. It is a CFD simulation, the steady state simulation. And the result is pressure as we see it here. And we also have vectors of the velocity at the surface. Let's see how we can map this result. First the pressure, and then we'll see the velocity. In ANSA, this is the target model. We will work on the Nastran deck as the target here. We go to the Structural tab and activate the results mapper. From the source format, we again switch to solver files, and we can browse to find the CGNS file, that is the source. We directly pick the CGNS file here, and by clicking Scan Solver File, Meta will be launched on the background, and it will be searching for any labels available in this file. Now that the file was scanned, we can see that there is only one state here, and we can go to the custom mappings and activate one new custom mapping. For the type, we can choose a scalar here, and we will go to choose the pressure and generate a boundary condition. Of type pressure. Interpolation method, we will keep it to common area because we are mapping from a surface to a surface, cell best to cell best, so common area can work with that. Shape function is also available, and RPF too. For the connectivity, we will type a question mark here and pick the target areas. And since this is a CFD simulation, and the source is a CFD simulation, and it is in meters, and the target is in millimeters, we have also to convert the units. We will switch from meter to millimeter during the mapping. This is now ready. If we click OK and apply, the results are applied, so we can see that some payload entities have been generated, and we can easily review them by activating the pressure frame spot here. Now we will deactivate the pressures and create a new results mapper for the velocity. We will pick the same solver file, scan the solver file again, and add effector result this time, and we will choose velocity, and the target will be a result entity. This is an auxiliary entity inside ANSA, which we can then use an API to get data from it and use it accordingly. We will just type a question mark in connectivity, pick again the same targets. We will switch the units again from meter to millimeter. And we are okay to apply this mapper too. By clicking Apply, we will have a mapping of the velocity at the surface of this area as a result entity inside ANSA. See that the result entity was created. And if we double-click on it, we can review this vector plot of the velocity at the surface. Now let's switch to the last example. Let's first review it in Meta. This is a deep drawing simulation. It was run with the Abaqus explicit solver. And we have three states of this forming simulation. We will hide the punch, the die, and the holder so that we can reveal the blank. And we see that for those three states, we see the blank deforming, and the results are 4 missing stresses in all through thickness integration points. We will map all those 5 integration points during the mapping process in ANSA. Let's go to ANSA. Now we have chosen the LS Dynadeck as the target, and we will directly go to the results mapper and choose the solver file. We can browse to the ODB file directly and click Scan Solver File to check what labels are inside this ODB file. For this specific case, since we have large deformations, we will use the deformed geometry flag here. We will activate the Use Deform Geometry, and we will add this time a tensile result, and we will use the full tensile ECS and all layers and centroid. As a target, we will choose a boundary condition of type stress. And we will leave the N-thick option to auto, so that all section points will be mapped by looking at how many are available in the source file. We will have to define also the connectivity. We will pick the target mesh here, and we don't need to make any reorientation. We switch off the reorient target mesh, and we click Apply. Once the mapping is performed, we can see that initial condition stress entities have been created. We can pick one and see that all 5 N-thick points have been filled with data. And we can also review this with a fringe plot again in ANSA. This time we can enable the von Mises stress fringe plot. And unfortunately, we're not able to see all the through thickness integration points, but we see the top and the bottom surface. The two surfaces depict the topmost and the bottommost integration point of the stress field. This was it for this demonstration. Thank you for watching.